Hey everybody, Professor Leach here. Today we're going to talk about simplifying expressions. Not in truly the traditional way. I want this to become from a matter of just reading what's going on in the expression and then taking this all the way back to our understanding of operations that we've been dealing with this whole time. So it's a matter of reading expressions and performing operations. So what I mean, I'm just going to just do death by examples. When we have something like, when we write x squared, we mean x times x. The exponent 2 is to indicate that we are taking two copies of x and multiplying them together. In the same way that if I write, say, x plus x, I write 2x. That came out backwards what I intended, but that's fine. When I write the expression 2x, I mean 2 times x, and that means x plus x. This has to bring to mind the rules that we had for these operations. Things that are going on here. This is 2 times x. This is multiplication. We're using multiplication is repeated addition. Multiplication is repeated addition. Here's repeated addition. We summarize that with a multiplication, 2 times x. Exponents are repeated multiplication. Exponents are repeated multiplication. Here's a multiplication of x times x, and so we write x squared. This will help us start simplifying expressions. The rules for simplifying expressions are not just randomly put together to try to cause you discomfort. They are the way they are because that's how numbers work. So if I want something like, if I want to simplify something like 3x plus 2x, we could encode this in some rule. We just add the coefficients. But when we look at 3x plus 2x, of course it's 5x because 3x means x plus x plus x. And 2x means x plus x. And we're adding all those things together. So of course it's 5x. Not by some rule handed down by algebra teachers, but what we mean by 5x, what we mean by multiplication, and what we mean by addition. It's just the way it is because that's how the numbers work. Same thing with exponents. If I have x squared times x to the third, it's not x to the fifth because when we multiply things with the same base, we add the exponents. It's x to the fifth because x squared is x times x. X cubed is x times x times x. And so if I multiply those, I'm multiplying 5x's. So of course it's x to the fifth. It's handy that we can just add the exponents, but that's not where the rule comes from. It comes from what we mean when we write exponents. Take two things and then 2 copies of an x and 3 copies of an x and multiply them all together. You're multiplying 5x's together. Any questions? Okay. So we just have to combine all these things together. So the other things that we have to know is that multiplication distributes over addition and exponents distribute over multiplication. So multiplication distributes over addition. And exponents distribute over multiplication. This is one way that we might be able to deal with parentheses. So these two statements are in the category of dealing with parentheses. This will help us understand how to deal with parentheses. Maybe this is where we take one expression and we replace it with a different expression. So multiplication distributes over addition. What we mean is that if I have, say, 5 times 2x minus 3, this multiplication can be applied to everything inside. That's the 5 times 2x minus a 5 times 3, otherwise known as 10x minus 15. The multiplication distributes over the addition. I know it's subtraction. Subtraction is just addition of opposites, so it follows the same rules as addition. Exponents distribute over multiplication. What that would look like is if I had an expression like 3x say to the 5th, all being squared. That means I should square the 3 and square the x to the 5th. So I can say this is 3 squared and x to the 5th squared. So we have different things going on for how we deal with the exponents and how we deal with the coefficients. 3 squared is equal to 9. And x to the 5th squared is x to the 10th. Now, this does not come from some rule where we multiply things, multiply the exponents. Say the whole sentence. When we raise an exponent to an exponent, that's not really what we're doing. When we raise an expression with an exponent to another exponent, we multiply the exponents. There's not a good sentence for that. You see this, you multiply them. That's not where it comes from. X to the 5th squared literally means x to the 5th times another x to the 5th. 5x's and another 5x's, we're multiplying 10x's. We can get away with saying 5 times 2 is 10, but what it means is that there's an x to the 5th times another x to the 5th. That's why it's an x to the 10th. And the exponent is distributing over the multiplication. Since multiplication distributes over addition, on a related note, division also distributes over addition. So if, for example, I had something like, I'll do the light blue again. If I had something like 10x squared minus 5x, and I wanted to divide this all by 5x. Dividing by 5x is the same as multiplying by 1 over the product of 5 and x. So I can distribute the 5x to each of the terms in the numerator. Oops. Although I need to spell it correctly. (10 divided by 5, and now we're just dividing. 10 divided by 5 is 2. X squared divided by x, if I have 2 x's and divide by 1x, one of the x's cancels out. And something divided by itself is equal to 1, as long as those things aren't 0. And since exponents also distribute over multiplication, we can also distribute exponents over addition. So if I have 3x to the 5th divided by y squared, and I wanted to square this whole fraction, I could square the 3, square the x to the 5th, and square the y squared. 3 squared is 9 because we're multiplying 3 times 3. X to the 5th times another x to the 5th, there's going to be 10 x's, so x to the 10th. Y squared squared, there's 4 of them. So 9x to the 10th over y to the 4th. We're not following some weirdo rules for algebra. This is just how numbers behave. This distributing distributing with division is helpful. So if I wanted to do something like 84 divided by 2, I could take half of the 80 and half of the 4. So sometimes we can divide in pieces. 80 divided by 2 is 4, or 40. 4 divided by 2 is 2. And so we get the 42 that we probably knew going in, but that helps us confirm that we can do this kind of operation. Any questions? Great. So the operations that we want to perform when we're doing simplifying expressions are the same operations that we want to perform when we're doing arithmetic. So one of the problems that we encountered on our quiz with exponents was an x plus 5 squared. And for those of you who didn't get this problem yet, I said, instead of thinking it as some weird different thing, remember what x plus 5 squared means. X plus 5 squared means x plus 5 times another x plus 5. And to do this multiplication, we have to do the same thing we do with arithmetic. It's the same thing as if we had 15 squared and we read it as 15 times 15. We'd have to multiply the 15 times 15, and we could do that in the normal way. 5 times 5 is 25, 5 times 10 is 50, 10 times 5 is 50, 10 times 10 is 100. So there's our 100, 125, otherwise known as 225. So we got to do the same thing. What we're using is the distributive property. So this process is the distributive property. Multiplication distributes over addition. That's what's going on when we multiply the 15 by the 15 over here. We're using the distributive property. Each term in, each digit in one number multiplied by every digit in the other number. That's us using the distributive property. So since that's what we do when we're multiplying numbers, that's what we're going to do when we're simplifying expressions or multiplying polynomials in this case. Each term of one polynomial multiplied by every term in the other polynomial. So the other variation on multiplication distributing over addition is each term in one polynomial by every term in the other polynomial. Polynomial just being a combination of powers of x and numbers. So we're going to do the same thing. We have an x plus 5 times another x plus 5. Just like here, 5 times 5 is 25. 5 times 5 is still 25. Where we had 5 times 10 for 50 in our number example, 5 times x is 5x. Then so I've multiplied everything by 5, or every term in the top polynomial by the 5 from the bottom polynomial. Now I do the same thing with x. X times 5 is just 5x. X times x is an x squared. And we're not doing anything new. We're just adapting something that we already knew. We already know how to multiply numbers. we use the distributive property. Multiplication distributes over addition. And to do that, we do each digit in one number by every digit of the other number. In the polynomials, each term of one polynomial by every term in the other polynomial. Same problems. In addition to all this, we have to remember the order of operations, not PEMDAS. PEMDAS is trash. We just have to remember that exponents go before multiplication unless parentheses. Exponents before multiplication unless parentheses. And multiplication before addition unless parentheses. The parentheses mean multiplication before addition unless parentheses say to do the addition before the multiplication, or because multiplication distributes over addition, we can also use the distributive property in that case. If I've got multiplication and addition combined in the opposite order with parentheses, I can use the distributive property. Similarly with exponents. So we got to think about the order that we're going to perform operations. So one of the examples I had was, one of the problems that we did was, let's say 3x squared times 5x all to the second power. Bad way to phrase it. We have the product of 3x squared and the square of the product of 5 and x. I'm going to try to speak things properly. It really comes out clunky. English is kind of a terrible language for math, which is why we have math in the first place. But what we have is we've got a multiplication and an exponent, and the exponent should go before the multiplication. There's multiplication here. And we have an exponent out here. So I'm not multiplying 3x squared by 5x because the 5x has an exponent attached to it. So the exponent is going to go first. So 5x squared, I can square everything inside because exponents distribute over multiplication. So 5 squared is 25. X squared is just x squared. And then I multiply the 25x squared by the 3x squared. This multiplication is the multiplication that we started with. That's the same multiplication. Now, when we're multiplying things, 3 times 25, I can just multiply those parts. 3 times 25 is 75. X squared times an x squared is an x to the fourth, because there are 4 x's that we're all multiplying together. The last thing I say that I have to say about this particular operation is like we multiply the things that we can. So 3 times 25 is a 75. And then I just pick out the x's to multiply, the x squared and the x squared to multiply to the x to the fourth. And this is what we do anyway. If I have, say, 2 times 3 times 5, I have a bunch of things multiplied together. Multiplication is what we call associative and commutative. Commutative means I can multiply in whatever order we want. So I can change the order 2, 3, 5, 3, 2, 5, 2, 5, 3, 3, 5, 2, 5, 2, 3, 5, 3, 2. There's 6 possible orders here. And they're all the same. Associative means I can group them however I want. So I could say 2 times 3 times 5 is equal to 2 times 3, which is 6 times 5, which is 30. Or maybe it's 3 times 5 is 15, times 2 is 30. Or even I can jumble the order. 2 times 5 is 10, times 3 is still 30. I can multiply whichever ones we want. When we're looking at 3x squared and 25x squared, I have 1, 2, 3, 4 things all being multiplied together. The 3 and the 25 I can combine into a 75. That's why I combine those things into 75. Not following some fancy rules. I'm just saying, oh, I'm going to choose to multiply the 2 and the 3 and write 6. X squared times x squared, I'm going to put those together because we can. X squared times x squared is x to the 4th. 75x to the 4th, until I know what x is, that's as far as it'll go. So here we are done. But we're not doing anything fancy. We're not following some weird arcane rules where we have to be wizards to understand what's going on. We're just doing the same operations that we always do. A further example of this 2 times 3 times 5 business, if I have something repeated like 2 times 3 times 3, I can read that as 2 times 3 squared. I can take the things together and I can summarize repeated multiplication with an exponent. And I can say that 3 squared is 9, and that's 18. Or I can just 2 times 3 is 6 times 3 is still 18. Or 2 times the other 3 is 6 times the left out 3 is 18 still. So we can gather up the things that are the same and summarize with an exponent. And that's all we're doing here, gathering up the 2x squareds, the things that are the same, and summarizing them with an exponent to make a simpler expression than what we started with. Any questions? This is what makes doing these problems in my class more difficult. I drop them all on you at once. This is what my hope is, that this makes it a little bit better because we're really working on reading expressions and deciding what we can do rather than just seeing something and reacting to it. We're trying to we're trying to leverage the big advantage that we have, and that we're in a safe environment. No lions are going to jump out and murder us, or mailman not going to jump in the house and murder us. So we don't have to react just on instinct. We can stop and think about what the expression means, and then proceed based on some rational plan that fits with some kind of rule set. Not because there are some weird arcane rules. That's just how numbers behave. That's what I want this whole class to boil down to. Performing operations, because that's how numbers behave, not weird arcane rules. This is not weird or arcane. It's just difficult to write. Any questions? This is where the class gets a little bit weird and rambly, because a lot of things start coming at you from different directions. One of the quizzes coming up, excuse me, is also an operations quiz, and it's going to involve some fractions. And you're going to go, ooh, fractions. But I'm going to put those problems in context, so you should be able to see what to do. If ever you're stuck on one of the problems on my quiz, look at the problem right before it. If that problem just involved numbers, they're probably related in some fashion. All right, that's going to do it for today. Tomorrow, on the 820 section, we will talk more about simplifying expressions, do a couple more examples of things. Go back and revisit those quizzes, even if you got all the problems right. Go back and revisit those quizzes through the lens of just perform operations. What is this operation? What is this expression asking me to do? And how is that just performing a bunch of operations? Work on reading and writing expressions. All right, that's going to do it for today. I'll see y'all on tomorrow, or at least Friday. Everybody have a good day. Thanks for playing, and peace out.